Hey there, folks. We are back and ready to take a look at some homework out of 5.1. we were only really able to do problem 5 today in its 5 parts because we spent a little time talking about these different characteristics of some relations, but that was okay. It was good learning time. That's fine. Let's take these up. Relation S. And we're going to talk about these different relations and then talk about, okay, what's the domain, what's the range, is it reflexive, symmetric, transitive, antisymmetric. So this first one is the relation S on the set 1, 3, and 5 with these ordered pairs in there. Okay, so when we talk about the domain is actually everything that's included as a first coordinate in these ordered pairs, so 1, 3, and 5. So the domain here is actually the set, not S. I was looking at this, but I wrote that. My bad. 1, 3, and 5. It's the entire set. Okay? And then the range is the set of everything that appears as a second coordinate. So 3, 5, we already got 5, I already got 3. So 3 and 5. Alright. Now, reflexive checks to see if we've got everything here as an ordered pair with itself. We don't have that. We don't have any of that, really, right? So the answer here is no, since, and we just need one counterexample, so I'll go with the first one. Since 1, 1 is not an element of S. Okay. Remember, these are these conditions for reflexive, symmetric, transitive, and antisymmetric are for all, right? For all elements of our set. So when we, even if we find one, if it doesn't work for every element here, then it's not going to count. Now, symmetric, we have to start checking conditions. Symmetric says if I have the ordered pair AB, then I've got to have the ordered pair BA. So immediately I see I've got 1, 3, but I do not have 3, 1. So this is also a no, since 1, 3 is in S, but 3, 1 is not an element of the relation. Okay? All right. Then transitive, we can kind of check on this. I've got 1 going to 3, and then I look for anything else that 3 goes to, 5. So 1 should be able to go straight to 5, and I do have that. 1 goes to 5, and then 5 goes to 3, so I should have 1, 3, and I do have that. 3 goes to 5, so again I'm going right here. And then 5 goes to 3, so I should be able to take the shortcut straight to 3, and actually I don't have that ordered pair. So this is not transitive, and that is my counterexample. No, since 3, 5 is in this relation, and 5, 3 is in this relation, but 3, 3 is not. Okay, and there may be another counterexample. Let's see. 5 goes to 3, and then 3 goes to 5, and I don't have 5, 5 either. So that would be another counterexample. All right. Notice that just because these things happen once, you know, if it doesn't happen for all, it doesn't have that property. Okay. And then antisymmetric says that the statement of it is, okay, if I have A related to B and B related to A, then that means that A and B must be the same element. But the fact that I've got this one ordered pair that kind of reverses itself, right? I've got 3 and 5 and 5 and 3, but 3 and 5 aren't the same element. So it's not antisymmetric either. No, since 3, 5 is in the relation, and 5, 3 is in the relation, but 3 is not equal to 5. Now this is different than these other things, right? This then part has nothing to do with the relation itself. It's just saying that those elements have to be equal, and in this case they're not. Okay, so that's 5A. Coffee break. Excuse me. Let's take a look at 5B. The relation R on the natural numbers is defined by and let me step back to this for just a moment, because the one thing I did want to do is kind of graphically draw this relation, because I think that helped us today when I did this. 1, 3, 5, 1, 3, and 5, and really I don't have to put the space between them. It could be like A, B, C, that don't go on a number line. But so when we look at this relation, we've got 1, 3, 1, 5, 3, 5, and 5, 3. Okay, and a lot of this relates to this imaginary kind of diagonal line, right? It's not reflexive since I don't have any one of these 3 points that would be on the diagonal, right? But just the fact I'm missing one of them blows it up. Symmetric, no, because here's 1, 3, but I don't have 3, 1, just on the other side. And then anti-symmetric, no, because I do have this point where I have 3, 5, and then 5, 3. Okay, and then transitive is probably not as easily shown on a graph, but these other 3 are illustrated quite well if you can do that. My puppy dog is awful cute. You'll be all right. I'll pet on you in a minute. It'll be okay. All right. So let's look at this one, the relation R on natural numbers defined by x is related to y if and only if x is less than y squared. So what's the domain? Well, I think we can get all the natural numbers into this position. Certainly 1 can go there, 2 can go there, and on up. There's no biggest number that I have to worry about staying below. So that's all of the natural numbers. Okay, and the range would be everything that can go here. I don't think that there's a natural number that's less than 1 squared. So I don't think we're going to have an ordered pair with 1 in the y's position. But certainly I could have that if y is 2, and so on. So either state this as natural number minus the 1, or range is the set of x such that x is a natural, no, I shouldn't use x maybe. B such that B is a natural number and B is greater than 1. Okay, something like that. B. So is it reflexive? Well, can I put 1 in here? I don't think so. Right? The fact that I have to take 1 out of my range is a pretty good tip-off. 1 is not going to be less than 1 squared. So no. Since 1 is not an element of the relation. Or you could write 1, and here's your R, and then mark it out 1. Since 1 is not less than 1 squared. And I think that may actually be the only thing that's not in there. 2 would be less than 2 squared, 3 is less than 3 squared, and on and on. So I think the rest of them would be there, but since we don't have this one, it's not reflexive. Symmetric. If x is less than this squared, is y then going to be less than x squared? And I don't think that's going to be true either. Let's see. Well, no. I mean, this is going to tear it up right here. No. Now let's think of a good one here. Was less than 2 squared. Yeah, that'll work. So 1 is related to 2, since 1 is less than 2 squared. But 2 is not related to 1, since 2 is not less than 1 squared. Okay, so it's not symmetric, and I'm sure there's other examples. Transitive, I think, also fails to work. Let's think about this. I think the example I used before. No. In fact, I almost had convinced myself that this did work, but actually it probably doesn't. I think the one I used before was 8 was related to 3. Okay, and I'm taking something that's very big here against something that's just barely big enough for 8 to be less than the square. This is true since 8, maybe this is another way of saying it, since 8 is less than 3 squared, which is 9. And now let's look at 3. 3 is actually related to 2, right? Since 3 is less than 2 squared. But I don't think 8 is going to be related to 2. Since 8 is not less than 2 squared. Okay, and there's probably a ton of other examples, but that one actually is all you need. If we're showing these things don't work, we just need a counterexample. So, and antisymmetric. Really won't work. Let's see. 2 and 3 are actually good examples. No. Since 2 is related to 3, that's because 2 is less than 3 squared. And 3 is related to 2. Since 3 is less than 2 squared, but 2 and 3 aren't equal. And that's what antisymmetry does. Forces those things that are apparently across the diagonal from each other, like this, to actually be on the diagonal. So if we were to draw this, and I do want to take just a moment and think about what this would look like. 3, 4, 5. 1, 2, 3, 4, 5. 1 we said was not on there, right? The rest would be, so 2, 2, 3, 3, 4, 4, 5, 5, and on. 2, 1 is not going to be, in fact, 1 we've talked about won't be in the range of this at all. So nothing down along here. 1 is less than 2 squared, it's less than 3 squared, 4 squared, 5 squared. 2 is less than 2 squared, and less than 3 squared, and 4 squared, and 5 squared. And then 3 is less than 2 squared, actually, and everything above that. And then let's see, at 4 is not less than 2 squared, but it's less than 3 squared. And then 5 is less than not 2 squared, but 3 squared. And so on and so on. So you see you're getting kind of a collection of points up here. But in particular, when you're thinking about that diagonal, we're missing 1, 1. So it's not reflexive. It's not symmetric because I have this point here. Is that the one I used? 1. Yeah, well, 1, 2, but not 2, 1. There's also, I think here, 1, 3, and not 3. I'm sorry, yeah, 3, 1, and so on. So there's several examples there. And then anti-symmetric. Yeah, we've got things that do cross this that aren't equal to each other. So there you go. Okay. 5C says, okay, we've got a relation T defined on 0, 4, 7 with these ordered pairs. The domain, we've got 0, we've got 7, we've got 4, so the domain is the entire set, 0, 4, 7. The range, we've got 0, we got 7, we got 4, so that's the whole set. Reflexive, do we have all the ordered pairs with themselves? 0, 0, 4, 4, 7, 7, we do. Yes, that is reflexive. Since there's just a small number, I'll write them out. 0, 0, 4, 4, 7, 7 are all elements of the relation. Symmetric. If we have things that are different, I've got to have the reverse. So 0, 7, do I have 7, 0? Yep. These aren't, flip those over, get the same thing, same thing. So yes, that is symmetric. And that's really enough to say. Transitive, let's see here. If so it goes to 0 and 0 goes to 7, we go straight to 7, right? 0, 7, 7 to 0, we got that. 0 to 7 and 7, 7 takes us right there. And then 4, 4 never has that kind of thing to check for. Nothing comes to 4, goes away from 4. So yes, that's going to be transitive. And then anti-symmetric, well actually these two we talked about will mess up the anti-symmetric thing. So no, since 7, 0 is, or 0, 7, whichever, is in T, and 0, 7 is in T, but 0 and 7 are different things. Okay, so again, if we want to draw this, and I'm not too concerned about spacing, 4 and 7, 4 and 7, oops, 7. Then we've got 0, 0, we've got 0, 7, which is up here. We've got 7, 0, which is right there, and 7, 7, and 4, 4. So we've got everything possible on the diagonal. That's the reflexive. We've got everything here. If we flip it over, this matches this. These things are on diagonal, so yes. Transitive, we ran through the cases. Anti-symmetric, no, because I do have a couple things here that do match up. And everything else is along the diagonal, so it's fine. Okay. (5D), we have the relation U defined on integers, saying that x is related to y if and only if the product is positive, which means that things have to have the same sign. They can't be 0, right? So the domain, I certainly can't let 0 is an integer, but I can't put it in here because that will mess up this inequality. So the domain is all the integers, but take out that 0. And same thing on the range. I can't let y be 0 either. Okay. Reflexive, x related to x, I have x squared, which as long as I'm not taking things that are 0, that would be positive, right? So yes, we do have reflexiveness. Symmetry, let's see, symmetric. If x is y, then y is x because this is commutative right here, right? So yeah. Oh, wait. You know what? I just completely botched this one, and I'll tell you why. This is the domain, but reflexive has to work on the whole set. What was I thinking? Right? It can't just work on the domain. It's got to work on everything in Z. So this is no. 0 is in the set. So since 0, 0 is not in U, that's not reflexive. I don't know what I was thinking there. I'm sorry. I kind of like someone today in class. I'm thinking about functions. Yeah, with a function, whatever your set is, that's your domain. Not true with relations. Okay, so it's not reflexive. It is symmetric. Transitive. If we think of this in terms of, and I certainly couldn't, I can't use 0 in any of my things here. These are ifs, right? You have to meet these conditions. So if I take two things that I could put in my domain and range, A and B, and I get this, that means A and B had the same sign. And then maybe B is related to C, well that means B and C have the same sign, which means A, B, and C all have the same sign. So A has the same sign as C, so that would work. Right? And then anti-symmetric, can I have things that are, I think there's a whole host of counterexamples on this one. No, since, what do you want to use, 1 and 2? Since 1 is related to 2, and that just simply means 1 times 2 is positive, and 2 is related to 1, that just means that 2 times 1 is positive. Actually, those are the same thing, right? So, but if this were anti-symmetric, it would force 1 and 1 to be equal, or 1 and 2 to be equal. Okay, and they're not. And I kind of drew this one for you in class too. This is the one that I drew wrong at first. These are lattice points. So on in the first quadrant, and then also in the third quadrant, right? You get it. Okay, but nothing on the axes. Okay. And then one last one, the relation P defined on z minus 0 by x is related to y if and only if the greatest common divisor is 1. In other words, things are related if they're relatively prime. Okay. Well, I can certainly put all manner of things in the domain of that. If it's not prime itself, say it's a composite number, then you can make, there's certainly things over here in the y that would be relatively prime to it. So z minus 0, and same thing on the range. Okay. Now, is it reflexive? Let's say we have x. Is x related to x? Well, unless x is 1 or negative 1, no. Not necessarily. I mean, well, not at all, right? If it's something like 2 or 3 or something like that, then the greatest common divisor would be that number. So no, since I'll just use 2. Since 2 is not related to 2. And what I mean by that is the greatest common divisor of 2 and 2 is 2, which is not equal to 1. Okay. Symmetry, we should have symmetry because it really doesn't matter what order they go into this, right? If A and B are relatively prime, then B and A are relatively prime, right? And then transitive, I think you'll find doesn't work. Let's think of an example. 2 is related to 3, and that happens because the greatest common divisor of 2 and 3 is 1. And 3 is related to 4. Greatest common divisor of 3 and 4 is 1. But can't go from 2 to 4. 2 is not related to 4. Since the greatest common divisor of 2 and 4 is 2. Okay. And then anti-symmetry. Well, there's a whole host of reasons this wouldn't work because it is symmetric. No. Since, how about 2 and 3 again? Since 2 is related to 3, meaning that they're relatively prime, and then 3 is also related to 2, meaning the greatest common divisor of 3 and 2 is still 1. It doesn't matter how we put them in there. But 2 and 3 are not equal to each other. Okay. So, not anti-symmetric. Okay. That's really all we got done today in class. We will come back and work some more of those on Tuesday. I'll also sometime here, hopefully tomorrow, if not tonight, get another lecture. I want to say a little bit more about relations. And so that'll be our next little bit of stuff. And that's probably all we're going to have time for then before our next test. Our test is 2 weeks from today. All right. And I will see you in class next time.